Okay, good evening and welcome to this last lecture. First, I will give you again this attendance sheet. I would appreciate if you plan to submit 1 or 2 or 3 more reports, please just write in the last column that you intend to do this, because for me, it helps me to just have an idea about how much time I need still to work on this. So just give me an indication. It doesn't mean you're obliged to follow exactly what you write here, but it just helped me to organize my time. Thank you. And a second thing, which I find quite interesting, this week there is a conference in France, and I decided not to attend it, but one colleague went there, and he knows that I'm teaching stochastic calculus, and he took a picture of one slide of another colleague, exactly on our topic. So I'm quite happy, and he sent it to me just for me to have a look. You can have a look. Now you should be able to understand this slide, which is really written by a researcher. It's probably the first slide of a presentation, but it's written by a researcher working on this topic, and probably this slide is not correct. So if you find what might not be correct, I would be happy, but it's not easy. But at least you should understand what it's about, because it's exactly our topic. So I just gave two things. I will maybe put this on the website for those who are not here. And finally, the lecture notes are completed. They are available on the website. I might correct a few mistakes in the future, but essentially it's a final version now on the website. So if ever you are interested, you can download it. All right. Last thing, evaluation form. Don't forget, for all courses, you have to fill some form, evaluation form, and it's important. Last week, we introduced and discussed this application to finance. So first of all, I gave a very simple definition of what is either a put or a call option, and we have two types, European and American. Of course, there are other types, and in fact, I'm only going to deal with European because they are simpler, but I just gave the definition. These options are related. You have the price that you give at a certain time t. The price is called exercise price. You have the maturity time, which is exactly when this option ends, and the payoff is the money you receive if you possess such an option. And in the simplest case, it has this formula. I will recall what is the meaning of this, parentheses with a plus later. I introduced this last time. And now, this was for a very simple introduction about options. Now we introduce the notion of market model. So market process is a collection of n+1 stochastic process. They all take value in R plus because they represent the price of something, of an object or some quantities. So they take value in R plus, and they satisfy some stochastic differential equations based on a standard Brownian motion. So there is a Brownian motion which is behind everything. And I gave one example, and I will finish with this example today, of the Black-Scholes model, which is a very simple example of this market model. This represents the price of some assets. Now you want to buy or sell this asset, and this is called the trading strategy. So the trading strategy is a function depending on time and on the underlying probability space, which is below this Brownian motion. It takes value in R n+1. What does it represent? Each entry is a quantity of one asset. So the 0 entries, I start at 0, represent how many of this asset you have. The first entry represents, the number 1 associated with 1 represents the number of this asset, and so on. So the value of your portfolio, simply your portfolio, is the number of one asset times the price of this asset. And as I mentioned, we accept any fraction, even real portion of one asset. We could deal with fractions, but it's of course simpler if we assume that we can buy just a tiny piece of chocolate, no matter what is the size. Okay, I introduced these 3 notions of self-financing, admissible, and arbitrage. Self-financing means you do not add new money in your portfolio, or you do not remove money from your portfolio. You just keep the total money constant. Admissible means we don't accept that you have no more money, so you have to have at least 0, but not a negative number. On arbitrage, an arbitrage is a strategy which allows you to get some money from nothing. There was a precise definition. And of course, an arbitrage-free market is a market model where you cannot get money from nothing, because in a model, this is what we expect. And then I introduced the notion of discounted price process and discounted portfolio. What is it? The 0 entry represents the asset which is risk-free. It is when you put your money on a bank account and you receive 0.01% of this money. So this is really, you take no risk, but still your amount of money is slightly changing over time because of this very small interest rate. So the discounted price process is when you divide the other one by S0, because it's relative to this possibility of not taking any risk. So this discounted price process is S1 divided by S0, S2 divided by S0, and so on. And the discounted portfolio is when, again, you take this, but you divide by S0. This is understandable. Then I introduced a notion which is slightly more complicated, this equivalent martingale measure. First, I had to explain what are two equivalent measures. I introduced this last time. And equivalent martingale measure is a measure equivalent to P, which is related to the Brownian motion, but which has a certain property, is that whenever you take some expectation of this S tilde is a discounted price process, you get a martingale. In a sense, you change your measure in order to have better properties on the S tilde, so on the discounted price processes. It's a technical thing, but it's a mathematical way also to get some of these notions more precise. For example, it can be shown that if such a measure exists, then you have an arbitrage-free model. In fact, it's even an equivalence if you are in a good framework. So it's very useful to have this tool. I will not come back to it too much today because it's slightly technical. And so now we come back to options. So an option is defined by the payoff, what you receive at time capital T, at the maturity time. We say that, and I did this picture, which I like. You have the time T. This is some money, and you expect these are random variables. So you expect that the price is around here, or it has a certain distribution. And you look for a strategy which allows you to cover exactly this price. Oh, you don't start at 0, but maybe you start at a fixed point here, which allows you to attain or to reach this random variable at time capital T. So we say that this option is attainable if there exists a strategy which is in a certain class of strategies. This doesn't matter. I introduced it last week, but it's a certain strategy such that at time T, you get your portfolio is exactly this. Why is it interesting? Because suppose you are the guy who wants to sell an option, take the position of the one who creates an option. You want to be sure that the market would give you at least the same amount of money. This is the idea. It would give you exactly this payoff. And so we call it attainable if you can do this. And then there is this surprising result that if you compute this quantity, which is not simple, but this is the expectation computed with this new measure, then this quantity gives you the value of the portfolio at time T such that you reach this condition. So it gives you exactly this trajectory. It gives you one of these trajectories. And in fact, it can be shown that this is a correct price to give for your option. So if you want to fix the price of this option at a certain time t, as a seller, you should give this price. Why? Because if you sell your option at a higher price or at a lower price, somebody can make money, can get arbitrage. So this person can get money from nothing. So this is not what you want. And so this is the correct price. So I start from here again today. So it's called the right price for this option at time t. And you can see it depends on all the evolution until the time t, because this is the information available. So it's the best price you can give to the option with the information available at time t. And I will make this even more concrete in an example later. So as you can see, of course, we are interested in having attainable options, because if we have this, we can give a correct price or the right price. And so maybe I just mentioned it last week. There is a definition. A market model. Market model is this family of asset price. A market model is complete. So the best you can do is complete if there are two conditions. The first one is that there exists P star, an equivalent martingale measure. And again, why is this interesting? Is if you have this condition, then it's an arbitrage-free model. So you cannot create money from nothing. And the second condition is that for any star, I'm obliged to state it like this. I said there exists at least one, but maybe we have more than one. So now for any of them, for any option Z T, so this is a payoff, this is a time of maturity, there is a technical condition that the expectation, this random variable has to be L1. But this is technical requirement. Any option like this is attainable. It's a definition. But again, what is the interest? Is that this first condition means it's a market-free or arbitrage-free market. Free market. And this, the fact that it has this property means you can give the right price to any option. Sorry, I should mention, it's not an arbitrary option, it's a European one. We are in the simplest case, European. What is the difference for European? The definition is you can only sell or buy it at time capital T. For an American one, you can, by definition, you can do it at any time between 0 and capital T. And you can imagine it's more complicated because you have this freedom. So we say that the market is complete if these two conditions are satisfied. And of course, we are interested in models when it is complete. And now you can see how I have been too cautious because I said for any P star, with the first line, I cannot say that there is only one, but it turns out that there is only one. But I couldn't say it before. It's a proposition. If the market model is complete, then P star is unique. So, and there exists a converse, again, with slightly more condition. There exists a converse statement. But this is more difficult. You can guess that it's more difficult because you have to show that there exists a unique measure having some properties. And okay, it's not an easy way, it's not an easy thing to prove. There exists a unique measure, and that it implies that then the market measure is complete. So I don't state it more precisely. Okay, so any model, and quite often they take it for granted, you are in a model which is complete because this is the best situation. You can give a price to all European options, and you have, it's arbitrage free, so you cannot create money from nothing. All right? Oh, probably the lecture today will be shorter because I don't have so much material, but you can take this opportunity to ask questions. Have you all seen this slide I gave? Can anybody say what is a mistake? I told you, if you can find a mistake, I give you a good grade. Okay, have a look. Okay, so up to now, it was a general theory. If you come back to the framework, it was introduced in section 7.2. The stochastic differential equation for SI, they were quite general. We had n plus one stochastic equations. They were quite general. So now I introduce what is called the generalized Black-Scholes model. So it's slightly more general than the standard Black-Scholes model. A generalized Black-Scholes model. So the stochastic differential equations, we have n plus one of them. The stochastic differential equation for the risky asset they are of a certain form which is less general than the general theory. ESRT. I will explain again what it means. I let you write and I will explain again. This, by the way, this term is called the drift. B is always the drift. And this guy is called the volatility. Bless you. And let me underline these two terms. So why is it less general than what I introduced in section 7.2? Look, in 7.2, I just gave one name for the stochastic process here and one name for the stochastic process here. Now I'm more precise. First, I factor SIT in both. Why I factor this? Because in the Black-Scholes model, this would be just a constant times SIT. And this one would also be just a constant times SIT. So in a sense, I factor what appears in the Black-Scholes model. And these BI of two variables are not completely arbitrary standard model, arbitrary stochastic process. They are a function of T, but of ST. So it's a differential equation. You don't have an arbitrary stochastic process here. You have a function of ST itself on the same here. So this is really less general than the general formula of section 7.2. Still, it's more general than the Black-Scholes model. And what is this N? Remember, we have a Brownian, n-dimensional Brownian motion, which is visible here. We have a sum over J from 1 up to n. It means we have n degrees of freedom, in a sense, capital N degrees of freedom given by these n independent Brownian motion. And this is true for, I mean, these stochastic differential equations are for I is equal to 1 up to small n. So we have two n, the capital one, which gives us a number of Brownian motions, and the one with small n, which is a number of assets. And I should also say that, of course, ST is ST1, ST2 up to STN. So this is a generalized Black-Scholes model. I still need to say something about the regularity of this function and the regularity of this function. So let me write a few remarks first. As I said, the factorization of this SIT is suggested by the Black-Scholes. I just write BS for Black-Scholes model, which I have introduced last week. So writing these two factors first is suggested by the Black-Scholes. Now, what about the regularity? B. Look, B has n components, so I can consider it as a vector. So it's going to be a function from 0 t, this interval of time, times Rn with value in Rn because it has n components. And why this Rn? Simply because, look, this St has also n components. Now you could complain. I could put a plus here because S taking values in R plus, But if I do this, I have to be careful about derivative, you know, when you have a closed interval. So there is no restriction in putting Rn. Even if the function takes value in R plus, it's not a big deal. And what is sigma? Can you tell me what I should write for sigma here and there? If I look at it as one function, it's a function of time, so 0t. And again, these n random variables. And what is its value? If it has two components, it's a matrix. Its matrix has two components, so it's in M. What are the dimension? What is the dimension of this matrix? Look, the first entry is between 1 and small n. So it's n times capital N. So it's not a square matrix. It's a matrix of n line, small n line, capital N columns. And then you can take its components, and you have I between 1 and small n and j between 1 and capital N. And what kind of regularity? I assume that they are bounded. Plus, you can close your eyes if you don't like it, locally Lipschitz. It's slightly stronger than continuity, but it's not differentiable. So it's something between, you can check, I gave the definition, but it's something between continuous, it's more than continuous, it's less than differentiable. If you take it differentiable, it's enough. Why we impose these kind of conditions? You know, when we have a differential equation, they do not always exist a solution. There are some differential equations with no solution. But it turns out that with these conditions, these n differential equations have n solutions. There exists a solution for each of them. So it's a theorem which more or less follows from what we have seen. These conditions imply there exist solutions S1 up to Sn of these differential equations. So does anybody find the mistake or what is not precise in what I gave you? Can I have one copy? Oh, I gave two. Or can you bring it back to me?
Is it that the time is continuous, but the plot?
No, this is okay. So for those online, you can probably not see, but I show this picture, which is a slide of a presentation at a conference. So at least you should have been able to read that we have indeed a stochastic differential equation. And it's about the Brownian motion. So it's exactly what we have studied. But it says, thanks to Ito calculus, there exists a unique continuous solution. Try to remember, when we wrote a differential equation, we had some conditions on the coefficient, like here. I'm not saying nothing on this coefficient. And on this slide, it's only written they are smooth. So it means C infinity. But if you check what we have written, you need some growth control. If it grows too fast, probably there is no solution, or at least not a solution on the entire time, maybe on a small interval. So probably, of course, when you do a presentation, sometimes you simplify the statement because you don't want to say all the details. But saying that it has a unique continuous solution is probably too strong. without any assumption about the growth of this or about the interval of time. Just keep this in mind. But yeah, the rest, you should be able to understand the statement. But we are in the good situation. Look, I assume that this function, they have some regularity, and especially they are bounded. So I am in a framework where we have a statement saying there exists a unique solution, which even it has even a certain regularity. Si is in M2 of 0t, which means we can take it second moment. But this is less important. But at least we have a framework where this differential equation has a solution. Linear algebra. You have all attended linear algebra 1, probably 2, or even linear algebra 3. What means that a matrix, oh, let me do this slightly different. What does it mean that a matrix n times n is positive definite? If you haven't seen it, it's good to see it. What means it's positive definite? This is true, but if I don't want to introduce the eigenvalues, there is this, I introduced this notation on purpose that I will record. What is it? What is this notation? You take your matrix, you apply it to a vector, and take the scalar product with the same vector. Probably you are more familiar with this psi transpose A psi. This is the same. Psi is a vector. So for any psi in Rn different from 0, I don't take the vector, which is 0, 0, 0, then it's positive definite if this quantity is bigger than 0. And in fact, indeed, it corresponds to all eigenvalues are strictly positive. Now, I don't have only one matrix. I can consider the same psi A of Tx psi, the positive definite. Oh, let me write it back. Maybe I wait a second before you write, because it's a little bit surprising what I'm doing. Instead of one matrix, I want to consider a family. And this family depends, like everything on my blackboard, of two variables, t and x, which is in Rn. But you know, if you assume that this is true for all of them, this can approach 0. You have any function, even if at every point a function is bigger than 0, you can have something like this. It approaches 0, and uniformly, you cannot say it's bigger than 0. So we say that this, or we impose that this is bigger or equal to a certain lambda times the norm of psi squared. So I should write, if this is bigger than lambda times the norm of this for some lambda bigger than 0, and all, now this is important, on all Tx, it's in Rn, and this one is in my interval of time. If this is true for all t, we say that A as a function, be careful, now it's a function, is uniformly positive definite. So please understand the difference. If you do it for one matrix, it's easy. When you have a huge family of matrices, just asking positivity is not enough if you want to have a property for the entire family, because it could approach 0. Even if it is never 0, it could approach 0, and you wouldn't have any space between 0 and the minimum value. So we say that it's uniformly positive definite if this is bigger than a certain lambda, strictly bigger than 0, times this chi square for all x and t. So it's this. No, I think it's understandable. X is going to be a point in Rn. That's why I took a difference between x and xi. Xi is in Rn. X is also in Rn, but they have nothing to do. And we also say for this, it's also called uniformly elliptic. It's another word for this situation. This is a very important fact. Be careful when you have a property for one point. If you want to generalize it to an infinite number of points or to a continuum, you have to be a little bit careful because you can lose a property. Therefore, the maximum and the supremum are equal on a finite set. Okay. What is my goal? So we have a slightly smaller framework. So now we are in this generalized Black-Scholes model. And I would like to get the notion of completeness because I told you this is the best framework. And I decided to present this because I like the coming proposition. We'll see. Assume n is bigger or equal to small n. So we have more Brownian motion than the number of assets, more equal. We also assume that sigma of T x, it's no more, but sigma is a matrix which is not square. So the is of rank n. You should have seen what is the rank of a matrix. So it has maximal rank because it's a capital N times small n matrix. So it can only be of rank small n, but this is a maximum one. And I assume that, look at this product, sigma times sigma t. It's a product of two matrices. What is the dimension of this product? Yes, but which n? Which n? Small or big? Correct. This is no, in fact, it's not one matrix. It's called a field of matrices. So it's a function from 0t times Rn to indeed n times n, but small n matrices. And I assume that this is uniformly elliptic, uniformly elliptic. This is exactly what I introduced there. It depends on one variable in an interval, one in Rn. We need that it's positive definite, but in a uniform way. That's not so strong. You know, in the one-dimensional case, sigma is just a positive constant. So we assume that we are not so far from a positive constant. What is the outcome if you're in this framework? Then there exists at least one P star. Remind you, P star is an equivalent martingale measure. And I also remind you that this implies that the market is arbitrage free. So we are quite happy. And the second part of the statement, if n is equal to n, then P star is unique. And we can write more, and the market model. Let me add one sentence, and then I would like to have your comments on this statement. So I add one more sentence. If capital N is smaller than n, so it's not in this is the end of the proposition, but this is just after it, then there might exist an arbitrage strategy. Please think about this blackboard. What does it tell you? Again, think about the Brownian motion as a random variable on the which exists, something you have no control on. If you have n assets, small n, and exactly this n independent Brownian motion, in a sense, you have an equilibrium on the degrees of freedom. Think about the degrees of freedom. You have the same number of degree of freedom between the number of assets you can buy and the number of independent variables. This is the best of situation. If you have too many random variables, you lose uniqueness. So it's still not so bad. On the other hand, if you have not enough freedom, there is a way to get money from nothing. You can play against the number of degrees of freedom. I think it's quite interesting if you think about it. The number of freedom is, so this capital N is a number of freedom for the market itself, and this one, this small n, is the number of assets you can buy. And you need to have this equilibrium. The number of assets should be exactly the number of degrees of freedom. But we will be, or we are interested in this situation when exactly small n is equal to capital N, because this is a most natural situation. In a sense, it also says that your n assets you want to buy are independent. You can also look like this. They are independent of each other, or you have enough independence between them. They are not too much correlated. They are not correlated, or not too much. Okay, so in the future now we assume capital N is small n, and we also assume that we are because this was an assumption for this statement, we have to assume it. For n is equal to n, this guy implies something about the rank. So we also assume that the sigma t is uniformly elliptic. It's enough. So best situation. Why? Because here we have arbitrage free market. No way to get money from nothing, and completeness. And completeness means you can give a right price to all European options. This was the definition of completeness. But there is still a problem. You know you can give the right price, but you don't know the strategy to follow this path. So remember this picture. You know that there exists a way to do it, but you don't know how you need to invest at any time to reach this situation. So there is still a question, but how to construct the trading strategy, which is denoted by H, the trading strategy, such that at time T, capital T, your portfolio is equal to a given option. This is a given option. You know it exists, but usually existence theorem is not enough. You know something exists, but how to get it or how to reach this point. So this is the next question, how we can get this. Do you have any question? I'm not sure you can get rich after this lecture, but we can understand a little bit more about what is going on. So we want to answer this question, how to define or how to get any information about capital H. Of course, when you have a question, we need some assumptions. So we have a small technical assumption. You remember S0 was given by this integral exponential ERS. Was this? It was this risk-free asset. And I haven't imposed anything about this RS. It was a interest rate, but it could also be a random variable. So we have to assume something. So this is just a reminder. We assume that RS or RT is a function of two variables. What is important is, again, this ST. And in fact, I don't like it because I don't find it very natural. What does it mean? Think about it. S represents the risky assets, so the things which change according to the market. And you are saying that the money on your bank account depend on the risky assets, which is not completely natural. I understand. I will show you why it's necessary to assume it. But in fact, so this is an assumption, but we can have, and this is probably the natural solution. We can have RT is simply a function of T. There is no contradiction. It can be independent of the second variable, like a function which does not depend on the second variable. So at most, it is a first situation, but it can be that just the interest rate on your bank account is just a function of T and nothing else. So it is included. because I don't think the first option is really natural. But okay. Plus, and we need plus, the function t goes, oh no, just a technical assumption, the function tx goes to R of tx, again Lipschitz. Some continuity, a strong notion of continuity. This is a small thing. So let's be in this framework. This is the last assumption. Oh, then remember Z is a random variable representing what the payoff, what you receive at time capital T. In the simplest situation I introduced last week, it was simply this function st minus k, a fixed number, plus. And what is this? It's a max between k and st. And yeah. But we can assume something more general. This was a simple situation. We can assume that this is just a function of st with h from Rn to R plus and satisfying h of x is smaller or equal to c. What is this? This is just a condition about the growth. It says that this function at most grows like a polynomial. Does the first function satisfy this? Look at this. It was one-dimensional, this function. Oh, no, it's fine. Oh, do I do a mistake? Sorry, I do a mistake. It's one dimension. Oh no, sorry, there is maybe a mistake in the notes. When I introduced this function, this was for n is equal to 1. So this is just one number. Look at this function. How is this function? Look at this function. You should think about the function x goes to x plus x minus k plus, and this function looks like this. You have 0, k, and as long as you are below k, it's probably like this. And, oh no, it's k. Sorry, it's not 0. But still it continues. So you have 0, you have k. So as long as it is below k, the value is k, and then it's linear. Then it goes like x. This is the function, this function. So it's in n is equal to 1 here, n is equal to 1 in this situation. It satisfies this linear growth. What? You don't think so? Take the max between k and x. So as long as x is smaller than k, the maximum is k. And suddenly you have equality, and then x is bigger than k. So it's x. It is. Okay, so what I mean is I can consider something more general than this. Okay. Did I say something about C and alpha? C and alpha are just constant bigger than 0, bigger or equal to 0. Yeah. If I did a mistake in the note, I cannot.
Your definition is wrong. Your definition itself.
Okay, so okay, but so the graph was the correct one, the one I wanted to do. It's 0. Okay, it's 0. Okay, so the mistake is here. It's max between 0 and st minus k. Okay, so it means as long as this difference is negative, it's 0. So sorry, the yellow one is this function now. Is it better? No, I hope now it's correct. You get 0 and then it's linear. Anyway, if there is a mistake, you can correct it. It's not difficult. Okay, so I mean, this framework, we have completeness, so we know that the right price for this option Z, I already gave the formula when I remind you at the very beginning, we have the right price given by a certain formula, E minus this integral. Let me change U S U U H of C. This is the formula I gave last week and at the beginning today, except that this was called Z. And probably, by the way, last week I did a small mistake. I corrected the note. This is, on the blackboard, I probably put 0, but in fact it is small t here. It's just a mistake. Now, you remember when we discussed a conditional expectation, I have written that, suppose for a second that it is not this, but it was a random variable. Let me call it for a second x, or not x, b, no, not b, y. For a second, I suppose that this is conditioned by another random variable. I wrote at that time, a long time ago, that this can be written as a function of y. It was what is called this Dubh-Dinkin lemma. Well, I didn't know at that time if I would use it again, but I mentioned it, Dubh-Dinkin. It says that if you make a condition with respect to one random variable, the result is a function of this random variable. So now we don't have only a random variable, but it turned out that this ft is related to st. This random variable st, the price at time. So the correct statement is this one. This is quite surprising and it's not trivial. Why is it true? Now, first you observe that it's necessary to have this function here, otherwise there is no chance this to be true. If it depends on something which has nothing to do with this, then it will never be a function of this random variable. And the second point is this filtration is not equivalent to the filtration generated by ST, except if you have this condition ST, sigma T transpose uniformly elliptic. In a sense, you can invert two things, and this fact that it's uniformly elliptic allows you to go either from the filtration in terms of FT, Brownian motion, or the filtration of this random variable. So it's rather technical, but it turned out that this expectation is a function of T and ST. This is quite deep. But this is a key of all this theory. The fact that this conditional expectation is just a function of ST. So this is rather important for what follows. And in addition, this P is a function. It satisfies PD with P from 0T times n satisfying that dt of p at tx plus lt, a differential operator at tx, minus r of tx p. This should remind you when we discuss the relation between stochastic differential equation and PDE. The conditional expectation was equal to a function of something, and this function was solution of a PDE. This is Feynman-Kac formula, or Fokker-Planck, or Langevin also has is of this form. And there is a condition, initial condition, is that P of T x is h of x. And you remember when we had this lecture about PD and SD, I told you apparently the final condition is more important than the initial condition. And look, we have the final condition in terms of h and not in terms of the initial condition. You want to focus something in the future, so you assume something in the future, and you want to know if in the future you are going to get money or not. This is the PDU. Again, this link between a stochastic differential equation and a PDE. And what is this LT? I didn't mention it. LT on a, I can just write it like this. It's a second order differential operator. We have already seen things like this. We have already seen things like this. If it is diagonal, we would be close to the Laplacian times this xi, xj, and so on. Probably we could obtain this formula from what we have seen in the chapter, but it's a little bit long to come back to this. Interesting. What we need to get the right price of an option is obtained by the solution of a PDE. So let me just write this. The right price for a European option is given by the solution of a PDE, something we have already seen. And what is the aim of this business? Remember, my aim was to find the strategy. Replicating strategy. What is a replicating strategy? It's precisely this strategy which leads you to the correct payoff can be obtained by hi at time t is so it tells you that the strategy is obtained if you can, by solving a PDE, of course, most of the time we don't know how to solve this PDE, but we have some numerical tools which give you this kind of function, solution of a PDE. Is obtained by taking just one partial derivative of this function with respect to I, and you get hi, and h0 at time t is obtained by minus this integral 0 t r of u su du times p t. Slightly more complicated, but if you get the n h1 up to hn, you can get also how much you have to invest in the asset-free or in the risky-free asset. So it's a closed formula. Once you have P, you can compute everything. I find something a bit amusing. This HI is also called or denoted by delta I of TST. This is also a name, delta. And people have defined other quantities. They have also defined something like this, gamma ij of TST. These are just definitions I give you for free. Just for the pleasure. There will be a surprise in a second. These are written in the notes if you don't want to copy. These are all the definitions. So what is this? That's a little bit surprising. We can take derivative respect to, this is a vector, or here you have a vector in Rn, so you can take derivative respect to first variable, second variable, and so on. So you can define partial derivative respect to j variable, partial derivative with the I variable. This is clearly called the gammas. So here you have the deltas. Here this is called the gammas. You can take the derivative with respect to t. And this is, of course, called the theta. Now, derivative with respect to r, it's slightly more surprising, but it's possible because the function p itself, look at the way it was defined, there is a r somewhere. So there is a dependence on r, which is not so explicit, but oh, there is a r somewhere. Yeah, it's a solution of a differential equation involving r somewhere. So there is a dependence on r. So you can also take a derivative with respect to r, and you can take, in the same way, a derivative with respect to theta. Here you have to be a little bit more careful because theta was a matrix. So I cannot tell you more. I don't understand. But why is it interesting is if you are trading, you get some information about the evolution of your portfolio according to these variables. So people call these the Greeks. Because these are Greek letters, even if Vega is not a Greek letters. And I put some additional names that appear in the literature. Okay. So apparently, I'm not reading, I have no idea about this, but apparently this kind of dependence are interesting because you know how your market will evolve if these parameters change. And that's quite natural. All right, almost the end. I want to say just a few more words about the Black-Scholes model, which is the simplest version of this. It's the last section, and I don't want to say so much because everything is already here, but we can be even more explicit for Black-Scholes model. So 7.6, Black-Scholes model. So the Black-Scholes model has only one asset, one risky asset, one unique risky asset. And of course, I'm not going to write S1. It satisfies just ds is mu st dt plus sigma st d dt. And this is constant. This mu is it's just a constant. This sigma is also a constant. And so I don't put the 1 because there is only 1. And the S0 is given by E minus T. Again, R is constant. So really the simplest case. And last week when I introduced this, I already gave the solution of, this is already the solution, but I also wrote the solution of this. Now, if we take the simplest payoff, the function with this plus I mentioned before with a mistake before. So for the simplest payoff, which was given by, it is V is equal to this ST minus K plus, which is a max between 0 and the difference ST minus K. Oh yeah, in my notes. Then remember in this case, this P, no, sorry, not P, this maybe I made a mistake. I don't know if I did a mistake in my notes or not. Everything was based on this. If I know this P, I can compute everything. And it turns out that for this model, we can compute this P explicitly. And let me give you one formula. It is not surprising that we can compute everything because the model is rather simple here. First, I write a rather complicated formula, but bless you. Okay. This is a computation. If somebody is interested how to get to this, everything is explicit. You can find the equivalent martingale measure explicitly and then compute everything explicitly. I cannot do it, but this is what you obtain. And okay, you may wonder how to do this integral, but it's not so surprising. It's not so difficult because look, as we have seen before, this function is 0, and not k, is 0 for a long time, and suddenly it's linear. So you can transform this into the same coefficient here, minus t minus t over integral from, let me write d0 of t minus tx to infinity of the same expression e minus z squared over 2dz. The same expression, but there is one big difference. There is no plus. I don't put the plus here. I put an upper bound. And what is d0? It's, you have to solve when this expression here is bigger than 0. Well, as long as it is 0, the function, as long as it is smaller than 0, this parenthesis is 0. When it's bigger than 0, then you just have the function itself. So what is this d0? Is d0 of t. I just call it at t and not at t minus t. It is 1 over sigma square root of t minus what is. I did this exercise. You can do it by yourself. Find when this expression, you just have to find when is this bigger or equal to 0. Wait. No, there is a small mistake. Can you see the mistake? I forgot something. There is a minus k here. So it's exponential of a long expression, everything minus k, because this is st. It was st minus k. And now it's meaningful because we have a k here while there was no k. So I need this to be bigger than 0. And yeah, you can already see why this logarithm of x over k will appear. You want this to be bigger than 0. You put the k on the other side. You divide by x. You take the logarithm. And at the end, you want to obtain it as a function of z. So when is this expression bigger than 0 as a function of z? It's a two-line computation. Okay. And now, once you have this integral, it's not so difficult because look, this term does not depend on z, so it's an integral of a Gaussian. And this, you need to work a little bit because you have a term in z and a term in z square. So you need to adapt and find a way to obtain a Gaussian integral. This is a rather standard. If you have not done any report or if you want to do one more, it's a good exercise just to work a little bit on this. And what we get at the end, we get that this is equal to x times a function phi, I will tell you what it is, of d1 minus okay, so what is this? You have a difference of two functions. One first function of a d1, a second function of a d2. What is phi? You can more or less guess. Look, when I have a integral of a Gaussian, but not from minus infinity to infinity, but from a certain point to infinity. So in fact, it's a cumulative what is it called? Cumulative distribution function. So phi of x is 1 over square root of 2 pi, integral from minus infinity to x E minus z squared over 2dz. This is called cumulative distribution function. What are D1 and D2? Again, it's longer to write these expressions than to really compute them. D1 of Tx is 1 over sigma square root of T. And phi T2. Okay. So everything is computable. And then, so let's just check that we understand every pieces. We have this cumulative distribution function. It appears quite naturally because we have integral of this, but not from minus infinity to infinity, which would give us 1, but partial integration. And then we have two expressions which are rather simple, and they come from this boundary we had before about this function with a plus. So once we have everything, it means we can compute all Greeks. And now it's even more explicit. Why? Look, this, it's no more visible. What we have computed here is P of Tx. This is what we are computing. The dependence on T and X are very explicit, but we can also see the dependence on theta and on R. So the derivative I mentioned before, which were less explicit, you can compute them. So really you can compute all Greeks, even the derivative with respect to sigma and the derivative with respect to R. So whenever you open a book which contains something about the Black-Scholes model, for sure you will see expression of this type, because this is really the solution of the Black-Scholes model. Okay. So if we summarize this part about finance, we understand more or less what is this market model, the different types of market model, the fact that we need this arbitrage-free model. Otherwise, it's a model where you can get money from nothing, which it's not sustainable for a long time. Maybe this is the model we live in, but it's not really sustainable. So market-free model, we need also completeness, because if you cannot get the right price for an option, then of course you are not going to emit this option. You are not going to produce it if you cannot give a price which has any meaning. And then, of course, we have again this relation between PD and SD and stochastic differential equations. But PD will give you some average or from expectation. But if you can compute this P, this function capital P, you have everything. And on this model, we can do it. This is only for European options. The one which can be, you can buy something and sell something at a precise time, capital T. If you want to deal with the American one, which you can buy or sell at any T, of course, you need more work. You need to, the theory is more difficult. So you need really to open a book which is only on mathematical finance. And this is not what we have done. I mean, we can understand now chapters in any book on stochastic calculus with one application on finance. The last chapter is usually application to finance. A book only about mathematical finance, we need one more course. That's all. Thank you. I know it was not an easy semester. I hope you have learned something. You should be able to understand now these kind of slides. As I said, the problem I suspect is there is not enough condition on the two functions, but it's a small thing. In the future, don't be afraid of opening a book on this kind of topic whenever it's necessary. We have already a few nice reports on the website if you look, and it's only when you do an exercise that you fully understand. I had a student this morning. It's only when in my office, it's only when we really work on a concrete example that, oh, things make sense and we understand what is going on. Just the theory, it's too abstract. Of course, we need it, but you need to put your hands in a problem in order to fully understand. And if you have any question, you can always come back to me. I will contact you very soon. If really you can work on 1, 2, or 3 reports. Oh, some are very optimistic. 3 reports, I would be happy. I need to give a grade. Of course, I'm not going to give bad grades, this is for sure. Still, I need something from you. I will, at the beginning of the semester, I said I will stop right after the lecture for getting reports. Of course, it's not possible. Still, I would appreciate to have everything by the end of January, or maybe 1st or 2nd of February, but not later. I mean, I don't want to, first I need to give the final grade before mid-February for sure, but I also don't want to extend this forever. Good luck for your future. Next semester is graph theory, if ever you are interested.